Did I do it? Did it ask you the question? Yeah. Okay.
Yes.
Share screen. Desktop. Okay. So I'm going to go to the PowerPoint. Okay, so to start off, does anybody have any like overall questions about like the axon or the dendrites or anything like that? Because that's
I can't think of any right now, but probably when we start going through it.
Okay. Where exactly do the neurotransmitters come out of? The terminals? The axon terminals or the dendrites?
No, the dendrite receives, so it like comes in through the dendrites, and then axon terminal is like away, so it sends.
Okay.
right here, it says like from the light yellow, it says the direction of the electrical impulse. So it'll go from the dendrite, just like she said, through the axon to the axon terminal, and then it will, she explained it, it will go through, it jumps across this little gap between that part and the next dendrite.
And that's the synaptic cleft, was that space?
Yes.
Okay.
Mm-hmm.
I was trying to find the word for that. I was like, I know she said it, I just can't remember it. A cleft. Okay. All right. So the next PowerPoint slide is basically explaining the resting membrane potential, and that that it's high in that potassium is high inside the cell and sodium is high outside the cell, and that basically the sodium potassium pump maintains that. And that the ions that she's talking about is the negative ions that are trapped inside the cell. I'm pretty sure. And then that all cells have the resting membrane potential. Some have, she said there's a range from -65 all the way to -90 or 85. Thereabouts is the range. And different cells have different resting membrane potentials, but the average that she wants us to know is -70. She explained also that some cells have the capability of becoming excitable, which that would mean like the action potential, and that's what she's talking about. And those have the ability to alter the resting membrane potential. Does everybody have like got a general concept of the resting membrane potential?
Yes. Mm-hmm.
Yeah. So the next slide is showing the opening and closing of the sodium channels. When do the sodium channels open or rush into the sodium ions rush into the cell? Does anyone know?
Threshold? No?
Well, yes, so that's threshold. When it reaches threshold, then the sodium channels will open, and then rapid depolarization of the cell will start. So good job. You got that. I don't know. I try. Okay. So like it says,
I feel like that'll be a question. Like literally, like what happens?
Yes, it will.
At this point in the action potential, I feel like she's gonna point out like a specific thing, and we just like have to know.
Yeah. So like on the study questions, the first thing that is on the sheet is happens at threshold, which is just like he said, the sodium channels open and depolarization starts to occur. So it's exactly what this is the first one.
Mm-hmm.
This is my internet connection is unstable. Can you guys hear me?
Yeah.
Yeah, we can hear you. It's just a little like choppy, but
I wish I could go get my phone and connect it if that would be better.
No, it's okay. You could just leave it here. We can still hear you, just sometimes it like lags a little bit, but it's not bad.
So the positive ions rush into the cell. So Na is positive, right, and it rushes into the cell where it starts to depolarize. Now, the term depolarization means that it's basically, she said that we don't need to know about polarity and all that stuff, but just to explain it a little bit more, it just means that it's getting closer to stabilizing the cell, which means like 0 to 0, like, and it gets like closer to 0. So at threshold, it's gonna go and hit a point, and then it's gonna so it's -70. And when those sodium ions start to come in, it makes it more positive or less negative to say. So it brings it closer to 0 that way. I hope I didn't confuse anyone. So just like it says, the cell depolarizes, and it's a decrease in resting membrane potential, and it's measurable by millivolts. Like I said before, the resting membrane potential average, I think that's wrong. I think that it's neurons are -90 or close to -90. Does anyone remember her talking about that? No.
That's what get me confused. On my note, I have -90, but I don't know why this one say -70. So I don't know.
I'll ask her about that.
Let me double check something.
Yeah.
Yo, you guys won't be able to see me because I'm at my patio right now. It's too loud
Okay.
inside, but y'all gonna hear me talking. Let me see what I have for that.
Question.
Yeah, I have like, wait.
Jackson, what was the question?
Actually, it's not a question. I was trying to figure it out, like what was -90 for.
Yeah. So I remember her saying that neurons were -90 or near -90 millivolts.
Cause like what I have is like I don't know what is it, but I have like when it -90, the potassium don't move at all. But I don't know what is the -90 for.
Oh,
Yeah,
the
-90 is the equilibrium for potassium.
yes.
It's for
So when it,
potassium.
So that
so when it overshoots, like in the
Yes.
action potential, it goes to -90. Potassium does, because that's the potassium equilibrium, like Melly said. And then the sodium potassium pump is gonna do its thing, and then it's gonna bring the -90 back up to -70, which is the resting membrane potential. That
Oh,
makes
basically when it's at -70, the thing is at rest, right?
Yes, always.
Oh,
It's always going to be -70 at rest. And when you
at
see
rest.
-90, that's the resting membrane potential for the equilibrium for potassium itself.
For potassium itself. Okay.
Yeah.
And I have here when it's above 90, like 91 or 95, it become more negative and potassium goes inside the cell.
Yes.
Okay. All right. When it's below 90, it's become more positive.
Uh-huh.
And then potassium goes out of the cell.
Yeah. And that's the chemical electrical gradient for potassium.
Oh, okay. So the -90, it's basically for the equilibrium, well, potassium, whatever, right?
Yeah, the equilibrium for potassium.
God's sake, this lady's gonna give all that question. All right then. All right, y'all keep continue.
Well, are you still confused? Because once we get to that slide, it'll probably.
No. I do understand it. I just want to make
Okay.
sure I don't get confused between the -70 and -90. So
Right.
now remember, the -70 is like when the membrane is at rest,
Mhm.
but the -90, it's a potassium don't move at all. So I just want to make sure the difference between like,
And what's the
the question
significance
right
of
when we keep going.
-55?
That's the threshold.
That's the threshold
okay.
voltage. Like
Right.
what?
Okay.
All right. Y'all keep going. I got it as we move along.
Yeah, so what I was talking about, I probably confused a lot of people. I was just talking about the specific to so every cell has a specific membrane potential. Does anyone have a question? I heard someone. Or was it just me? Okay. It was feedback, sorry. I was just talking about specifically to the neurons. I heard her say before that it was close to -90, but it might not be. So I'll check with her. But I don't think that's something we need to specifically know, like all the amounts for the resting membrane potential or average for each cell. So let's go to the next one. So this diagram just shows it's opening and closing the cell ion channels. Okay, so the next slide, it says changes to resting membrane potential. Positive ions into the cell or negative ions leaving the cell causes depolarization, which is excitatory. So she explained it a little bit at this point in the presentation, but basically it just means that when the neurotransmitter transmits whatever signal, it stimulates the I don't know exactly what, the cell membrane to reach threshold. And then when it's reaches threshold, then it causes depolarization because of the opening of the sodium channels. So this is excitatory because it's basically stimulating. I think that's what that means. So, and then negative ions into the cell or positive ions leaving the cell is inhibitory because basically it's stopping, right? It's inhibiting. It's stopping the, oh goodness, can't remember. Anyone want to jump in? Good. No.
It's kind of
So it's
confusing.
yeah, it's very confusing.
Yeah. Let me,
Hyperpolarization.
what I have, I just have like whatever she was saying in class, because I was in class that day. So the only thing that I have is like when the resting membrane potential, it's become more positive, it called depolarization and it decreased. So I just get confused between the ion thing. I don't know what the ion thing is doing here. And then I have when it's hyperpolarization, it's when the resting membrane potential is become more negative, and the VM is increased. VM, I don't remember what it stands for, but I'm pretty sure you guys familiar with it.
I know what you're talking about. So basically the negative and positive ions, what they're talking about is when it's talking specifically to action potential. So on the questions, because this is basically where I got all my thoughts together. One of the questions is, what is it?
It's much easier to understand when we have the graph. I feel.
So it says what is hyperpolarization? Hyperpolarization is when the potassium channels are slow to close, so they rush until the membrane potential is past -70 millivolts. So that means it hyperpolarizes, it goes past the resting membrane potential and is more negative than what it's supposed to be. So it inhibits I don't know, the action potential from affecting it, which I'm pretty sure it has to deal with the relative refractory period. But that's complicated. And I think just like she said that it helps when you have the graph.
Okay, so like for example, like what if I say like the question that she asked in this study got say what is hyperpolarization, right? So what if I put like hyperpolarization is when the resting membrane potential is become more negative and the MV is increased. So is that the same thing?
That's correct.
But I heard you read a different answer, like from the thing she say. I don't know if it's like.
Well, I was just describing it in the way that why it's inhibitory. It's
Okay.
just another kind of, so there's two questions here. What is hyperpolarization and why does hyperpolarization occur? So you could also give hyperpolarization is when the membrane potential is past -70 millivolts or more negative than -70 millivolts.
So basically, why is it occur again? Hyperpolarization?
Why does it occur? So hyperpolarization is when the potassium channels are slow to close. So they rush in until the membrane potential is past -70 millivolts.
When potassium, sodium are close?
Yeah, so but that's
Wait,
not
you
the
say when
potassium.
potassium, sodium are slow to close, right?
Yeah, but it's not it's just the potassium channels. The potassium channels are slow to close after repolarization. So it goes past -70 millivolts. and that's called, when it goes past negative 70 millivolts, it hyperpolarizes the cell. So that means it just gets hyperpolarized from the point of negative 70. So it just means that it's more negative. So the reason for it is because potassium channels are really slow, like her grandmother, and just take a long time to close. That's like what she used in the lecture.
All right.
But
So
it honestly, that's honestly pretty
Yeah,
hard
sorry.
to understand.
Sorry. Keep going.
It's actually really hard to understand without the graph. So when we go into like the steps of the action potential, it will be a lot easier.
I just
So do you
looked
guys
up,
actually think she's gonna give the graph on the exam? Because I remember her saying like all the question will be multiple choice, right?
I mean, she could still put a graph and then like, you know, ask a certain question on it, and that could be multiple choice, and we just kind of have to narrow it down to like, you know, what specifically she's asking. But I don't think she knew exactly if she was going to put the graph or not. I think she said she typically doesn't.
Yeah, that's what she said. But
Yeah.
Yeah, but regardless, it's easier to understand the concepts if we're looking at it.
Mm-hmm.
And I also looked up like the definition of inhibitory just to make it like a little more clear. It just says inhibitory effects on the neuron, they decrease the likelihood that the neuron will fire an action potential.
So that means just so later on when we get into relative refractory period, that's what she's describing, as it's going to take a lot more of neurotransmitter connecting to the receptor to shoot off to reach threshold. So that's just basically what it means. But that's like jumping way ahead of the gun in refractive, like the PowerPoint. Do you understand?
Yeah, I get it.
So then the bottom of this is return to resting membrane potential, so repolarization. So in terms of what we're going to talk about is threshold, depolarization, repolarization, then hyperpolarization. So those are like the 4 steps when it happens with the action potential. So it's kind of like out of order. So it can be confusing. Like this slide is confusing when you're looking at it now, but if you go back, okay, so maybe we can go back to this after. So this is just showing what it means. Depolarization is stimulation and hyperpolarization is inhibition. As you can see, the bottom part is depolarization. It's going towards 0, okay, and this one's going past negative 70. So this is basically more positive than negative 70 and less positive than negative 70, or more negative. Now I don't exactly know what this top part is. I'm guessing it's it's measuring the resting membrane potential of the axon, I'm guessing, but I don't really understand the graph that much on this slide. Does anyone else? Guessing that's what it's measuring.
No, she didn't really go over this one that much. She kind of just like skipped over it from what I remember.
yeah, you can move on to the next slide. She didn't really stay on this one.
All right, so gated channels responsible for changes to resting membrane potential. Gates control ion influx through channel, closed versus open. So the next slide, the next slide, literally shows. I'm pretty sure the inactive, the open, active, which will make
I'm sorry.
that makes a lot more sense.
Me, guys? I mean, I think you're breaking up. I mean, you look like you're on slow motion or something. I don't know if it's my phone, but
Probably me.
No, it's her
breaks up a
connection.
little,
It's a little laggy.
yeah. Oh, okay.
So let me
I thought that was on me.
go get my phone and like connect the connection. That's what I usually do, but I couldn't find my phone before this, so I'll go find it real quick and then I'll be back. But you guys, somebody could talk about this while I am gone, if they'd like to. No? Yes? No? Okay. I'll be back.
Are we gonna do the worksheet today?
No,
Worksheet what? What worksheet?
Just like
The
the
act-
practice worksheet with
there's a-
questions.
The one that she answered the questions?
Yeah.
Oh.
Personally, I didn't do it. I mean,
Yeah, I was like trying to
maybe we could do that like on our last Zoom call before the test.
The exam,
We could
yeah.
go
Yeah.
over all of the questions as like a review. Maybe that will be easier instead of going through like each and every slide.
Yeah.
So
That'll be good.
yeah, because I didn't even really
Like
look at
Thursday, we
it.
can do a review on basically everything.
Right.
Oops. I'm just a little worried how she gonna present this exam, you know?
Yeah.
When you feel like you study and then like it's confusing the way she's gonna ask the question. I know that for sure. Even
But then-
on the question sheet, like it's hard for you to understand the question until she explains to you or until she answers.
Yeah, you just have to find a way to like break down the question to where you understand it and actually, because they'll just throw in words to confuse you. You just have to actually figure out what she's asking. But I feel like we can only do our best, and we really
Yeah,
won't
of course,
know
of
until we
course.
take our first exam,
Yeah.
kind of what it's like. Because it might be hard for someone else, and then for someone else they could
It might
understand
be
it.
easy.
So.
Yeah.
Mhm.
No, I
think
mean,
it's
like, I
easy
don't
for
mind breaking it
anyone, but-
down. It's just like, when you're on the test, you don't have time to break it down. Because I
Oh,
think
yeah.
she said we have 1 minute and a half per question. So
Mhm.
I'm assuming
Right.
50 questions. By the time you had to take to understand to figure out the longest question, sorry, my language, by the way, a long question, like
Yeah.
you might be running out of time. But I'll do my best. We
But
always do our
also,
best.
this is like, I'm thinking about it this way too. Like, this is the first semester where they really had to like cut everything down.
Yeah, because of COVID.
Yeah. So maybe when people took her in the past, our test might be a little bit different. I don't know.
Yeah. Let's see.
I mean, they can't change it that much, but that's just kind of what I'm thinking. I'm just trying to stay positive and not stress myself out too much because I get bad test anxiety.
Yeah,
So-
me too.
And I
mean,
second guess myself a lot. But
and
anyways,
then to be honest, it's like next week I'm gonna start studying. I mean, I start studying the previous one or whatever, but I know I'm gonna do good in anatomy though, because it's not a lot.
okay, we can continue with the gated channel. Sorry, we got off track.
Okay, I had to go find my phone. I did not know where it was. I had to ping it with my Apple Watch. It was great. It's like a whole thing. All right. Closed versus open. So we get into this more later on because a lot of things can be very easily explained when you're talking about what happens when action potential happens. I just think that it's much easier to understand the concept than like specific definitions. Channel protein component. I don't exactly know what that means. I don't think she talked about it other than it's what is the channel called? Oh my gosh, I can't remember. It's the electrical something channel. Electrical impulse something.
Oh,
I don't
the
know.
chemical electro something.
Yeah, electrochemical.
Yeah,
Electrochemical. I said it the opposite.
I tried. We tried. Okay, so it's specific for a given ion. So the Na channels, which means the sodium channels, do not allow potassium in, which is it just goes back from what we talked about in previous times, where when we're talking about large molecules, that they have specific receptors for those things, and if they can, you know what I'm talking about, that they're specific to the ion. So potassium channels can only allow in potassium, and sodium channels are specific to sodium, but there's another ion that can't get in. But that's regardless of the point. They're specific to the ion. Sodium channels are all gated, yes, and they're closed at resting membrane potential. So they're closed. Now they can flicker open and allow some sodium ions in, which that's what causes it to be a little bit less than 90 when they talk about negative 90. That's what causes it to be a little bit closer to negative 70. That's why it's closer to 70. That's one of the reasons. That's just what it says right there. It counts for resting membrane potential being a bit more positive than potassium, because because these flicker open, it makes it more closer to 70 rather than 90, which would be the potassium equilibrium. That's what we're talking about.
I'm sorry. I remember she said that it's closer to negative 70 because potassium, it accounts more in the cell than sodium. Like it
Exactly.
contributes more to the cell than sodium.
Yes, so you're exactly right. It does, because potassium is more permeable.
Permeable, yeah.
Exactly. And that's exactly right. But because they can flicker open sometimes, just a little bit of sodium will get in the cell, which causes it to be negative 70 rather than negative. Exactly. You're 100% right. Potassium channels, some are gated, some are not. Some leak back out of the cell, but because of the sodium potassium pump, they get right back into the cell. And it accounts for the permeability of potassium. So I watched the lesson again, or the lecture, and she said that potassium was more permeable, like a total of 20 times. So I'm like 100% certain that's going to be on the test because she repeated herself so many times. That was fun. Couple hours. So this next, did anyone have any questions about the last slide?
No.
Okay. All right, so channel closed at resting membrane potential. So it's showing you a sodium channel. In the first panel up right here, it's showing that the channel is closed and it's active. So this one right here, channel's open by depolarization, which is action potential. So it's open and active. You see this little ball down here? So that's what causes it to be inactive. So this is depolarization when the sodium channel's open and sodium can rush into the cell. Now, if we go to the next one, it's channel unactivated. So it is open, but it is inactive. So that means that no sodium obviously can get in the cell. This is during the refractory period. So when we're talking about absolute refractory period later on, this is kind of what we're talking about. She said some of it's not totally responsible for the absolute refractory period, but it is partly responsible. So that's what it means. But we're going to talk about that later, so not to get confused. But as you can see, they're both closed right here. So you can agree, like she said in the lecture, that they're both closed in these two. They're not closed, but they're both, no ions can get into the cell, right?
Yeah.
Okay, so does anybody have any questions about this? No. So there's a lot on this slide. Action potentials: if inject positive current via electrodes, small depolarization decays back to resting membrane potential. So what that means is that, let's just say a tiny, a small electrical impulse is sent through, which means a neurotransmitter connects to, a neurotransmitter connects to a receptor and sends a signal. If it's a small signal, nothing will happen unless it hits threshold. And what will happen if it doesn't hit threshold is it just decays back to resting membrane potential. Does everyone understand that?
Yeah.
Okay. There's a large depolarization, a sudden dramatic change in the membrane voltage. Then, and if it reaches threshold voltage, then this is when the sodium channels begin to open, which causes, which is depolarization of the cell. Does anybody have questions about that?
No.
Opening of voltage gated sodium channels, that sodium will rush into the cell, depolarizing the cell, and it causes even more sodium channels to open over time. And eventually, when you reach peak, the peak and create an action potential, that peak is negative 30, which she just said that she didn't want, you don't need to know that, but I think it makes sense to me. That's a specific number. So it's negative 30. And when it reaches
Positive 30.
that, sorry, I can
It's okay.
positive 30. When it reaches positive 30, then these channels, the sodium channels, inactivate, which means that little ball that I talked about in the last slide or the slide before that, it goes up into the channel, and no sodium can get back and get in the cell. So just prior to that, the potassium channels will start to open, but again, they're really slow, so they take a little bit to open. So when they start to open, then they respond to depolarization. So potassium will come into the, right? No, yes.
No, it will move out of the cell.
It'll go out of the cell.
It will move out.
Okay, so potassium will move out of the cell, and
Mhm.
efflux.
That's when the membrane potential becomes more negative.
So positive potassium will go out of the cell, and it repolarizes the cell back to resting membrane potential. And because they're slow to close as well, it overshoots, and that's what causes the hyperpolarization, which means it goes below negative 70. And then eventually the sodium inactivation gates reset, which means they go back to a closed state, but the ball is not there, so it's closed but active. And the sodium and potassium pump will reestablish the gradients, so back to the resting membrane potential of negative 70. That was a lot. Thank you for correcting me. I sometimes get confused with saying it out loud is different than knowing it in your brain and then the connections. Anyways, does anyone have any questions about that? Yes. No? Okay. Great. So what this next slide is talking about is thresholds up here at negative 55 millivolts. And this is a stimulus, but it's not enough to reach threshold. This one is a threshold stimulus, so it does reach threshold and it creates an action potential. So this one is a bigger stimulus, but as you can see that the frequency is more, but the size of them, they're not bigger just because it's a bigger stimulus. There's more of them. You can see my dog in the background. Hi, Joy. So that's what they're saying. There's a question on the sheets that helped me with this. Well, I can't find it, but it's on here. And basically it's just a question about, does it have, I know where it is. Where is it? Okay, come on. It's free. See, I can't find it now, but I will find it eventually. Okay, it's right here. Excuse me. Do action potentials always have the same amplitude and the same duration? So the answer is yes. No matter the stimulus, if threshold is reached, which means if it reaches the peak threshold of negative 55 millivolts, the action potentials have the same amplitude and duration. Hi, baby.
They could just have different frequencies.
Yeah, the frequency is how you tell them apart.
And that was coding, right? What we were talking about
Yeah,
last night
yeah.
is okay.
Yes, so that's coding. And exactly like she said, so it's the frequency. So yes, so they're the same amplitude, that means they're the same height, the same amount, but there are more of them. So there's more action potentials, there's more that are fired or whatever. There's more receptor to neuron.
I just want to make sure I understand. So there, no matter how weak or strong it is, as long as it reaches the threshold, then So the way to tell them apart is by how many action potentials they're shooting off, right? Is that right?
Yes.
Yeah, I assume it's like, yeah, like they'll reach the same, but one would just last longer. That's how you know. It's hard to think about without like an actual example.
Yeah,
I
so
know.
it's not that. So they have all the same. Well, they all have the same duration, but the amount of time between them can vary. No, yeah. So the duration between when it reaches depolarization and goes. Yeah, that's a little confusing. Okay, there. Just because yeah, it's hard. But they
Wait,
all.
what's the difference between the question that says what happens at threshold and the one that's like what happens to sodium voltage gated channels at threshold?
It looked the same to me, to be honest. When I was
Yeah,
looking
like
at that question too, because I
1
feel
and
like it's the
4,
same in a
what's the
different
difference?
words. Yeah.
At threshold, the voltage gated channels are for sodium are open.
And active. Yeah, so it just more specific questions. So what happens to sodium gated channels at threshold? It just means they're open and active. And what happens at threshold? Sodium channels open and depolarization starts to occur. So just
Yes.
different types of saying the same thing. So
Okay.
like if you explain it for like I like that her tests are going to be multiple choice so that it's answered for you. So it's you can just pick the
Hopefully, yeah.
most correct answer. But that should be interesting. I don't think we've talked about how her tests are going to be hard. We don't know what they're going to be like until we take it the first time, and then we can kind of figure out how to study and how to plan. Like if it's super duper hard, then we'll have to obviously study more and be more on top of it. And if it's not as hard, then you don't have to worry as much.
For the coding part, some way I remember it is saying that when you have a bigger stimulus, the cell it stays depolarized more longer. You don't get bigger action potentials, but you get more of them.
Yeah.
Exactly. Yes, that's exactly right. Okay. So, does anyone have any questions about that? I know it's hard. It's hard on this graph to understand and explain. But for the most part, if you know that as long as it reaches threshold, they're all going to be the same size. Like there's not Joy. Sorry, my dog is angry. She wants to be out with the other dogs. So it's all more. Excuse me. It's all the same height of this, but there's more of them, just like she said.
Yeah, it's the same peak.
Yes, it's the same peak, but if it's a bigger stimulus, there'll just be more action potentials fired. Okay. So did she really talk about this? I don't think so.
Not really.
Yeah, I
No,
don't.
she just showed that it didn't reach threshold.
Yeah, I don't. Did she talk about this either? I don't remember. I don't think so.
She did.
A little bit, but I
Little bit.
can't like pinpoint exactly what it was. I think she was just showing us like it's a ligand binding thing, and that's what makes it open. If I don't know, correct me if I'm wrong. I remember her saying something about ligand binding in this picture. I know it says it too, but
Yeah. So from what I can see right here is a ligand activated ion channel, and the neurotransmitter will bind to the receptor on this channel, causing the sodium to rush into. I'm guessing that's what she explained, which causes depolarization of the cell. I remember her talking about autonotropic receptor / ion channel, but I think that means ion channel. So that's correct. So this is an ion channel. It's a ligand activated ion channel. So I gotta note that. Gotta remember that part. Ligand.
I think that was also on like the last thing that she covered on Friday. It was like metabotropic and ionotropic. And basically the ionotropic was a ligand-gated ion channel, like it literally says in that picture. And then the metabotropic was a receptor that is not a ligand-gated ion channel.
Okay. Yeah, I think I remember talking about that too. Yeah, we'll get to that. All right. So is everyone comfortable with this slide? Okay. Okay. In this slide, my Zoom is kind of blocking it. Okay. Basically, it's explaining. It keeps wanting to show up. Okay. It's explaining that how this works. So the stimulus is right here. It reaches, which just means that the neurotransmitter binds to the receptor and causes the depolarization of the cell to stimulus. So then it goes to -55, reaches, no, excuse me, sorry. I messed up there. Neuroreceptor binds to,
Neurotransmitter binds to a receptor.
neurotransmitter binds to receptor, stimulus channels, and allows for depolarization of the cell. Then at this point up here at the top of the graph where it reaches +30, then sodium channel will become inactive, means the ball just goes into the hole. The potassium channels out right here will start to open, but they're slow. So once they reach here, then the potassium rushes out of the cell and goes back, and the membrane potential goes back down here to -70. But because they're slow to close, they go past 70, reaching to, below 70. I don't know exactly how much. It says -90, but it might be a little less. And then the sodium, so then they'll close. And then the sodium potassium pump after they close will start to regain the membrane RMP. So they'll start to basically fix the gradient back to what it was before.
And when it's going down, that's the repolarization phase. Okay.
And this part down here, do you see my little clicker thingy? This part down here, when it reaches past -70, that's hyperpolarization. Exactly.
Got it.
So, all right. What else is? So
And
that's
I
just.
remember her saying from threshold. Hold on, I wrote it down. From threshold to the depolarization phase, that is the absolute refractory period, and then where it goes down to -90, that's the relative refractory period.
Yes.
I asked her.
Yeah.
I just needed like reassurance that was right. So I just wanted to put that out there. So because I was getting confused, like where exactly like those two refractory periods were taking place.
Yeah. So what she was just explaining is right here. It's from threshold, like you said, from threshold to -70. That's the absolute refractory period. And then below -70, when it reaches hyperpolarization, that's the relative refractory period. Am I correct?
Yeah, so when it first reaches -55 on like the sodium side, from there, once it reaches that -55 threshold, all the way to the depolarization phase until it goes to repolarization, that whole area is going to be the absolute refractory period. And then just that small portion where it like dips down to -90 instead of -70, that's the relative refractory.
Yeah, it's like anything above -70 is absolute, and anything under -70 is the relative.
Yes.
Yeah.
Okay, so is everyone good on this slide?
Yeah, I think so. Also, I saw this video and it's probably really stupid, but in case anybody gets confused where like the sodium side and potassium side are, just remember like salty banana, because sodium means salt and then potassium is a banana. I don't know. I saw that and I liked it, so I wanted to share.
Yeah, I like that.
Yeah, that's nice. And she mentioned it too, I remember. The salty banana thing.
I saw it on YouTube video, but I don't know if she mentioned it, but
She didn't, but like when you're in the middle of a test and you forget half your brain, it's so nice to remember something that's like kind of in your, like, I can remember that salty banana. It's something that you can just pull back from.
yeah, you'll just be sitting there laughing at your test.
All right, so I'm going to go to the next slide. So the next slide is just showing you the same thing as before, but more specific to the axon, which I don't think she went over that too much. Did she? Go over this?
Mm-mm.
I think she just took more time on the other graph that we were on.
Subtleties, I can't even say that word, but it's not even that hard. I don't know.
Subtleties.
Subtleties, yes.
Subtlety.
So it's just saying the sodium potassium pump only maintains the gradients. It doesn't produce any action potentials. She said that you don't need to know anything about cyanide or Wabane. And then it said potassium overshot termed after hyperpolarization, which just means that after it reaches -70, it goes further down below -70 to a more negative resting membrane potential. And it's important to the relative refractory period, which just means that during that time that basically it could reach threshold again, but it needs a bigger stimulus to do so. So if it's a very big stimulus, then it would go right back to threshold and do another action potential very quickly. But sometimes it's not a very big stimulus, so it will basically go under -70, and then the sodium potassium pump will reestablish gradients. I hope I didn't confuse anyone there. But it says discuss later, so we'll discuss it later. So this is the I can't remember exactly what it was, but the video that she showed us. Does anyone want to look at the video again?
Might as well. Oh wait, it's a long video.
I don't know. I can't remember.
When the cell membrane is at its
loud?
rest.
Is that really loud? Or is it okay?
I'm just gonna put my own
Yeah,
volume
I'm just
down.
gonna lower my volume a little.
Okay. All right.
Resting membrane potential, the activation gates of the voltage-gated sodium ion channels are closed and the inactivation gates are open. Voltage-gated potassium ion channels are closed. Depolarization is initiated by a stimulus which makes the membrane potential more positive, causing the voltage-gated sodium ion channels to start to open. As threshold is reached, many sodium channels open. Sodium ions diffuse across the membrane, causing depolarization. Voltage-gated potassium ion channels also begin to open, but more slowly. Therefore, depolarization occurs because more sodium ions diffuse into the cell than potassium ions diffuse out of it. As the membrane potential approaches maximum depolarization, the inactivation gates of the voltage-gated sodium ion channels begin to close, and the diffusion of sodium ions decreases. The potassium ion channels remain open, and potassium ions continue to diffuse out of the cell. The increased potassium ion permeability lasts slightly longer than the time required to bring the membrane potential back to its resting level. The extra efflux of potassium ions causes the membrane potential to become slightly more negative than the resting value. After the voltage-gated potassium ion channels close, the active transport of sodium and potassium ions reestablishes the resting membrane potential.
Okay, so does anybody have any questions about that? Hello? No? Did it kick everyone off?
No, we're good.
Oh, we're still here.
I was like, there's no one's talking. I'm just like, just me.
I'm sitting here like shaking my head and I'm like, oh, she probably can't see me.
Oh, same.
The PowerPoint went. Okay, let's see. All right, got it. Okay, so does anybody have any questions about that? I think everyone shook their head or something. No?
I
Yes.
think we're good.
All or none. So she talks about how you can either be pregnant or you can't be pregnant. So there's no middle ground. Once threshold voltage is reached, an action potential occurs. If it's below threshold, no action potential will occur. When an action potential occurs, the membrane reaches negative 30 millivolts, and the sodium channels will inactivate, which means that little ball goes in there, and they remain inactive until repolarization, which means that until the membrane reaches the resting membrane potential of negative 70, they will remain inactive, which corresponds with what she said, the absolute refractory period. So when those balls remain up in there, they can't activate. So you can't go back to threshold because no sodium. Yeah, get that? That's a little complicated. I probably didn't explain it too well. Amplitude of AP is the same regardless of initiating stimulus. So we talked about that earlier. So they're the same amplitude and the duration is about the same as well. So we talked about coding a little bit earlier that there'll be more action potentials rather than greater action potentials. Does everybody understand that?
Yeah, I think so.
Okay. So it's the weakest, and then this is a kind of medium signal, and this is a large signal, and this is the strongest signal. So you see that they all have the same amplitude. Here we go. And so greatest stimuli produces the same action potential coding, therefore not amplitude moderated, frequency modulated. Okay, so it means this is a medium, this is a small stimulus. See how it doesn't do anything. Weak stimulus, but it reaches threshold, will create some action potentials, but they'll be far apart because of the relative refractory period. And then these action potentials, it's a very strong stimulus, and they're very close together. Now they can't be any. Let's just assume that this is a very strong stimulus, and this space in between these, this is called the absolute refractory period. So it cannot be any closer to one another. They cannot be any closer to one another because of the sodium channels being inactive until the resting membrane potential gets back to negative 70 millivolts. Does everybody understand that?
What did you say about the middle one, like it only has 4 action potentials? What did you say about the refractory period?
So this would, yeah. So this would be relative refractory period, which just means that there is going to be a longer time between the action potentials because it needs to be a stronger stimulus if it's going to repolarize, if it's going to depolarize right at the end of the net. So it's pretty complicated. So let's just say the first one, it's going to go below and be hyperpolarized because of the fact that it needs to be a stronger stimulus to make it go right from negative 70 back to the threshold and make it an action potential. So because it's a weaker stimulus than this one, it's going to take longer to get back to that threshold and create another action potential.
It wouldn't be absolute refractory period. I'm just reading the definition and I don't know. So
Yeah.
they would both be relative refractory periods?
So this would be absolute refractory period. This is the shortest amount of time between action potentials, I'm assuming.
That's like the closest they can be.
Yes.
I'm still confused.
So let's just say we have a stimulus, okay, it reaches threshold. So threshold it's at negative 70 millivolts. Okay, so then it goes all the way to positive 30 because of the sodium channels. Then it starts to repolarizes and it goes back down to negative 70. In this case, okay, it's going to leave the potassium channels open for a little bit longer, and it's going to hyperpolarize, which means it goes all the way to close to negative 90. It's going to take a lot longer time to go back to threshold of negative 55 because they were left open longer, the potassium channels. Now, in this case, without explaining it all again, so when it repolarizes, because it's such a strong stimulus, right at negative 70 millivolts, it's going to go right back up to negative 55, which just means that because the sodium channels become active again at negative 70, that's because they can go right back to negative 55 if it's a strong stimulus, because it does not hyperpolarize.
Okay, I get it.
Yeah, that's really complicated. I bet there's somebody that could do a lot better.
Oh, no, that made sense. I just needed it gone over a second time. But just because there's a longer space between like the middle stimulus, there's like only 4 of them and they're pretty spaced out. It's going to take longer for it. No, I understand what you're saying. I just needed it repeated.
So she didn't go over this at all, and I don't particularly understand it that much. Did she go over this? I remember saying something about presynaptic.
No, I think she skipped that one. We didn't talk about that at all.
Yeah, I don't remember it.
Yeah, because I would remember the image at least, you know. That too.
So refractory period. Frequency has an upper limit, which just means that it has a limit into which how many action potentials you can have in a given time. As you can see right here, the time is going this way. Obviously in this one it doesn't reach threshold. This one it does, but it's not a very big stimulus. So there's space between them. Now in this one there's an even bigger stimulus, and there's even less time between each of the action potentials. And in this one it's an even bigger stimulus, but because it's such a big stimulus, if there's a bigger one, there still has to be some amount of time between when the action potentials are fired because of the absolute refractory time, which just means when the sodium channels are still inactive, they cannot be stimulated again. So they're inactive. That means that they can't do anything. So during that time, once it reaches negative 70, the sodium channels become active again, but they're closed, and then they can be stimulated. But during that time period when they remain inactive, when you talked about from the top of from negative 55 to negative 70, that's the absolute refractory period. There's no way that another action potential can be fired in that time because the sodium channels are still inactive. Do you understand that? Yes. Okay.
So the first one would be relative, and then the other 2 would be absolute refractory periods. Is that correct?
So in this diagram, these 2 are both relative refractory periods. You have to kind of assume from each diagram it's going to be different. So if it just depends what she shows, but this is supposed to be representative of absolute refractory period.
Okay.
So relative just implies that there can be more.
Yes, exactly. There can be more. And this diagram shows that there can be more action potentials fired. So usually it's the last one on the diagram that she wants you to know it's absolute refractory period, this one right here. Because this is the most that they're showing you can be fired off. And you have to assume that she means that this is the absolute refractory period. And this one is relative, and this one is relative, and this one doesn't reach threshold, so it can't even be considered.
So, because I'm reading over the absolute refractory period, and I have starred partially a result of sodium channel inactivation. Can you just go over that a little bit? I know we did that on the last graph, but I'm just trying to like make sense of it.
Okay, so in these two, basically, when you're talking about depolarization, the sodium channels are open. So when they reach the top or the peak, basically what happens is the sodium channels become inactive, and they will be inactive until negative 70 millivolts, which means back to when the resting membrane potential is reestablished because of the because of the potassium channels being open and the potassium rushing out. So from negative 70 millivolts, before that is reached, that means that there's no way that another action potential can be fired because they are inactive. Now, when it reaches negative 70 millivolts, I can barely talk, but when it reaches negative 70 millivolts, those sodium channels will become closed but active. So then if the neurotransmitter if the stimulus is big enough, it will immediately go back to threshold or as close as possible, try to reestablish threshold, and then go to another action potential and keep going like that. Now with relative refractory period, it's talking about that because the stimulus is not big enough, even though the sodium channels are active but closed, the stimulus is not big enough to depolarize immediately or reach threshold again. So the potassium channels will remain open, and they close slowly, which causes hyperpolarization. And it hyperpolarizes to about, close to negative 90. So it's going to take longer to get back to threshold. So it's going to take more stimulus to get it back. Do you kind of understand? I am not probably the best.
Kind of.
Yeah, it's very hard. I could probably explain it a lot better. If you watch this again, probably the first time I did it a lot better than that one, but maybe the next slide will help. Okay, so absolute refractory period, the time that a neuron is incapable of firing another action potential, irrespective of stimulus intensity. So she really emphasized that regardless of how big the stimulus is, in absolute refractory period, there's no way that another action potential can. So so she said that it's partly a result of the sodium channel activation. So like I said before, when it gets back to negative 70 millivolts, the sodium channels will be closed but active. And once that happens, then they can immediately, the neurotransmitter can send a receptor and open, basically reach threshold again. Then the sodium channels can open, and it happens very fast. So that can... But during that time period, when it's not back to negative 70 millivolts, it cannot fire another action potential. Do you understand?
Kind of.
Okay, so relative refractory period, another action potential can occur. So it's that during that period after negative 70 millivolts, where if the stimulus is big enough, it could repolarize. It could get back to threshold, but it doesn't because it needs a higher stimuli to do so. Do you understand that kind of? It says discuss shortly, so I'm guessing it's going to go back over that. Does anybody have a better way to explain that or anything? Okay. So this is the same graph as before. She puts it in here again to show what I basically do it again. So at resting membrane potential, the sodium channel is closed. So the ligand ion channel is closed. Now the next point, when the channel is open, because the neurotransmitter connects this receptor right here, I'm pretty sure, right about there, then the channel becomes open by depolarization of the action potential, which means it reaches threshold and it opens the sodium channel, and all the sodium ions can rush into the cell. Okay, and this little ball represents if it's inactive. So the next part is during the during the absolute refractory period. So when it reaches that peak status at the top of the graph, if you know what I'm talking about. The top of the graph, when potassium channels are open and potassium is rushing out of the cell, and sodium channels will inactivate, which it shows right here. This little ball swings right up into that hole and it closes off the sodium channels, which means that the sodium cannot rush into the cell anymore. Okay, and when these channels are inactive, okay, when they're inactive, that means that the absolute refractory period is happening. So that means that no sodium ions can get into the cell. So there's no way that it can become depolarized again at all because they're closed. Do you understand that? So this will remain inactive until it reaches negative 70 millivolts. Let's see if I can write. Ooh, let's see. A pen color, red. Okay. Negative. Oh, look at that. I've never done this before. I'm like a little kid. I get excited about the little things. Okay, so negative 70 millivolts is when this will open right here. Okay, so you see how it's closed, right? But it is active. Oh gosh, that was a little overshoot, but it's active. Okay, so during this period, then this can happen again, right? Channel can open, okay, and depolarization can happen again. So that means if it's a big stimulus, okay, then this part right here where channel is closed but active can happen faster, okay, which just means that there can be more action potentials. Oh gosh, look at me, little savant. Okay, more action potentials that's ugly. Okay, we're not going to talk about that, but more action potentials can happen in a shorter period of time, or just more can happen. Now, if let's just say we talk about this. So the channel, let's talk about relative refractory period regarding this. So let's just say we have a kind of okay stimulus. It reaches threshold, okay, and this happens, depolarization and action potential. So the channel's open, the sodium rushes in, okay? Then we get to the peak, they inactivate, okay? They inactivate again, and the potassium channel's open and potassium rushes out of the cell. Okay, so they'll rush out of the cell until about negative, they're slow to close, so they'll close about right around negative 90, okay? Now, it's gonna take a lot more time or a lot more stimulus to basically get that cell back to negative 55, which is the threshold. Okay, so that time period, it needs a bigger stimulus. It can happen if it's a big stimulus, but because it's not a big stimulus, it's going to take a lot longer to get back to this part, the depolarization, because it needs to reach threshold again. So that just means there's going to be a lot less of them compared to a big stimulus. So like, I can't draw, but 1, 2, 3, 4. Okay, so this is relative refractory period. You see how there's big gaps between the action potentials? There's a big gap there. Okay, that means that there could be more of them or more frequency. So let's just say that's an okay stimulus. So it's like right there. Okay, that's my little arrow. All right, so this one's going to be absolute refractory period. It's going to be really close together. Okay, and you see how there's going to be, so that's 4, 5, 6, 7, 8. Okay, 8. All right, so it's going to be a bigger stimulus. Okay, so let's just say in regards to these two graphs, this is absolute refractory period. The period between these two are very slim and there's more of them. Okay, so that means that as soon as it hits negative 70 millivolts, it's going to go right back to threshold, and then it's going to fire another action potential and another action potential, and it's just going to keep that repeating process because it's such a big stimulus. And it's going to stop eventually, obviously, right here. In this diagram, the ugliest diagram ever, it's going to take a much longer time to get back to threshold because it's going to go a little bit lower, okay, like down here. Like if I did like the little graph, it's going to go a little lower, okay, than negative 70, okay? And this part right here, below the line, below the line would be hyperpolarization. And in hyperpolarization, that's the relative refractory period, okay? So they could fire another action potential, but it needs to be a bigger stimulus to do so. During this period right here, when sodium channels are inactive, okay, it is not going to be able to fire another action potential because they are inactive. Okay, does that help at all? My ugliest diagram ever.
It did help. I'm just gonna have to rewatch it. But definitely it did help.
They did. I love the little, like, I've never done that before. Anyways, I'm just like a little kid. Anyways. Okay, so does anyone have any questions about that or want to elaborate any more? No? Yes. Okay. All right. So at resting membrane potential activation gate closes the channel. So like we were talking about before in this will probably help. In this potential, so the sodium is closed, but it is out right here at resting membrane potential. The activation gate closes the channel, and it is active though. Oh my gosh, look at me. Oh, it's the ugliest writing ever, but we're gonna active. Oh, that's not a V. Okay. Woo. I'm having fun. Okay. Okay, so that just means that sodium cannot get in at that point, but it is active, and that is when just this red line right here, it is at negative 70, and threshold is at
Negative
55.
55.
Negative 55. Okay.
Wait, so in this picture, it's saying it's closed but active or inactive?
Yes. It's
Okay.
active. See, so this little ball means that it's if it's closed, that would mean that it's inactive. But because there's no ball right here, in this hole where the diagram shows us because sodium can't get in. Right there. Do you understand that?
So it's the gate is closed, but it's active because the ball is away from the gate, right?
Yes. Yes. And what it's trying to say is that at resting membrane potential, which is negative 70, this line right here, that little line right there, that's what is happening. That the gate is closed, but it is active. Do you understand that?
Yes.
Alrighty. So this is just showing it again. So depolarization stimulus arrives at the channel. So, man, it'll probably arrive right there. That's what it showed in the other graph. And then it could reach threshold. And when it reaches threshold, that causes that, as you can see, the ball is not in the hole. So as this, oh my goodness, okay, right up here, that's what it's talking about. So that's what happens at depolarization. When it reaches threshold, it opens that sodium gate and it becomes active and open. So in this one right here, this is closed but active, and this is open, excuse me. This is closed but active. This is open and active, and this is open and inactive. Okay, we tried. Does that make sense?
Yes.
Or mouthful. All right, so with activation open, sodium enters the cell, and this depolarizes the cell and causes it to go all the way up to positive 30 membrane voltage or whatever that. So everyone understand this one? It's just explaining step by step what happens to the activation gate through the when depolarization happens and repolarization happens. Okay, so when we're talking about this, so this is the graph that we're talking about. Let's just say that's negative 70. This is threshold, reaches threshold about right here. Then it goes all the way up to the positive 30. Okay, then at positive 30, this point right here, what this is talking about is the activation gate closes, which means this ball right here, it goes up in the hole, okay, and closes this. And sodium cannot enter, but the gate remains open. Like the sodium channel remains open, but it's inactive. Do you understand that? Right here. Okay.
Yeah.
So the next one is repolarization caused by potassium leaving the cell causes the two gates to reset their original positions. So that just means that it closes again, okay, and it becomes active, which causes, which during this period, after it becomes active and closed, that would mean that the absolute refractory period is over and the relative refractory period starts. So at this point, once it closes and it activates, then another action potential can be fired if the stimulus is big enough. Do you understand that?
Yeah.
So then at resting membrane potential to activate closes the channel, just like I just explained. Sodium cannot enter and it's active. Okay, so that's at negative 70 millivolts. So activation gates responsible for the absolute refractory period. Ball and chain, block the channel following depolarization for set time interval. Okay. Channel in an inactive state, relieved upon repolarization after it reaches negative 70. Oop. Then it will become able to fire another action potential if the stimulus is big enough. Closed and active channels can be opened via depolarization. This occurs after the membrane repolarizes, which means after it gets back to negative 70. It can happen if the stimulus is big enough. So then it goes on to talk about relative refractory period. So it fire another action potential, but it needs a stronger stimulus to fire the action potential. Sodium channels are still open, so okay, and it hyperpolarizes. Okay, so it goes below 70, maybe up to negative 90, and more positive charges need to cause it to go back to threshold, which would be like right. This is 55, so it's like once it goes negative 70, it needs stronger stimulus to get back to potential, which means it needs just more positive charges. Do you understand what I'm saying? No, it's really complicated. I feel like I've said it over and over again that I don't even know what I'm talking about anymore. Does that kind of make sense? Ish.
Yeah.
Hopefully. Okay. All right, so as it explains right here, the inactive sodium channels, so right here, when the channel, okay, and down here, until it gets below or at 70, that's when active periods, period. Okay, potassium cell flow, more positive charges to set again and fire an action potential.
The audio is like weird for me.
See how fast this is? 10 seconds.
No,
Like
same.
that's a millisecond. Like this is so fast
You
in our
can't
body. We don't.
figure out what you're saying. It's like
Wait, did she
the
leave?
audio.
Maybe she disconnected and then she's gonna try.
Okay. Oh, it's still recording.
You all okay? You guys good?
Yeah, well, we're just, the connection got bad, so I think she's.
Yeah.
All right. All right.
So
I mean, like, it's still bad.
Yeah, I think it's still bad.
I can't hear a thing.
I'm gonna message her and let her know that. Oh, someone else is the host now?
I would attempt to pick up where we left off, but I was kind of zoned out, so I don't know.
I was about to message her and write, oh,
Okay, host now.
okay, it's better.
it's so what happened was my phone died, and that's what it was providing me the stable connection. So
Okay.
when
Oh.
it reverted me back to the Wi-Fi, which sucks. So sorry about that. I'm back.
No, yeah, it's much better now.
Yeah, definitely.
Okay. All right. Play from current slide. Okay. So, I was just talking about how crazy it is that the time period between them is like in milliseconds. So like this is like so small and we don't even think about it. I was just saying that, how crazy that is. Does anybody have questions about this slide?
I don't think so.
So this is what the last thing she talked about. So the neurotransmitter from the axon terminal to the dendrites, some binds to receptors, high specificity. Oh goodness, specificity. Neurotransmitters termed ligand. If synapse is ionotropic, it's an ion channel opening upon binding, which just means that, like what we've been talking about, the action potentials, those are ionotropic synapses. No. So the ligand gated ion channels are ionotropic, which it has to do with what we've been talking about all this time with the sodium channels, all those stuff, right? Because those are.
Olivia, did she say this in class? Did she go over this slide?
Yeah, but
Yeah,
she kind of like just know that the ionotropic is the one with ions and the metab whatever is the one without ions. She's like, just basically think of it like that.
Yeah, so the ionotropic is the ligand-gated ion channel, and a metabotropic is not a ligand-gated ion channel. The receptor is not a ligand-gated ion channel.
Right.
So I'm pretty sure that the metabotropic we're going to talk about next time, which has to do with protein signaling, and I'm pretty sure it has to do with the metabolism and sending signals like that, maybe like hormones or stuff of the sort. So because of the breakdown of the word metatropic, metabolism, that kind of is what it reminds me of. I don't know exactly what she's going to lead to, but I remember on the next slide, she talks about Well, I don't think we are, but this, oh goodness, okay. Where's my little pen? All right, gotta get that. Pen color. What do we want to do? Like cyan, magenta, cyan. All right, we're gonna do cyan. Okay, so this is a metatropic receptor. So this is not what we've been talking about this whole time. It's when this little ball goes in this hole, and then these are the G proteins that it's talking about. We haven't really talked about this at all, but what we have been talking about is this iotropic receptor, which this could be oh goodness, this could be the sodium. Oh gosh, I'm gonna do this, Na. Okay, Na plus. That's the ugliest Na I think I've ever seen. Just cross that out. I don't know where the.
This also, she mentioned it in class too. This slide.
Yes. Yeah.
Okay.
Yeah, I
Yeah,
think
she
this was the
briefly
last
went
slide.
over it.
I'm pretty sure this was the last slide.
Okay.
So what the the sodium channels that are opened as a result of reaching threshold, those are ionotropic receptor channels. Okay, so then like they fit like right here ish things, and then they connect or they go into the ions. Yeah, so the neurotransmitter connects to these little things right here. It doesn't really show it, but it shows it more down here. So there's like little, I don't think we need to know this, but they go right there. And then the ions will go into the cell after they connect, as you can see in this one. So the neurotransmitters fit in these little holes right here on the side of the ionotropic channel or receptors. Those are what they are. So then the neurotransmitters, the ions will rush into the cell, which would have been sodium in this case. Now, we haven't really learned about these, okay, at all, but just know that they're responsible. They have G protein, something like that, because that's what it says right here. If metatropic activation of G protein signaling. So we know that it has something to do with that. And she talked about that just a tiny bit. I'm pretty sure we're going to talk about it tomorrow, but that's the last thing that we need to know. The metatropic is the activation of G protein signaling. And the ionotropic is the ligand gated ion channels, which could be sodium, the sodium channels that we're talking about this whole time. So those are what those all are. That's kind of complicated. Does anyone have any questions? No. Yes.
Where are those ion that I can't even say the word, but where is it located in the nerve cell, in the neuron?
So they're on the, basically what they're talking about is like on the cell in the membrane, there are these ligand gated ion channels on the membrane that allows for, so when the neurotransmitter connects to the receptor on these ligand gated ion channels, then they cause, after it reaches threshold, they cause the cell to open the sodium channels and allow for depolarization of the cell.
Wait, so this is not happening in the synaptic cleft, or it is?
So the neurotransmitters diffuse across the cleft. They connect to the dendrites, I'm guessing. I don't actually know, but I know that they have
thing if synapse is ionotropic.
synapse. Yeah, if synapse. So yes, you're correct. So the synapses, I'm guessing, happen on. I don't need. I need a thing. Okay, so this is saying a cell. So I'm guessing it's a synapse.
I think synapse is the space between
the neurons.
Yes, between the axon terminal and the dendrites.
Yeah.
Where the acetylcholine would be, or I mean the neurotransmitter would be diffusing. I guess so. Yeah.
And once they diffuse across, or once they diffuse.
I'm sorry.
I don't know. I'm not really certain about it either. I hope she goes over it again. I mean, maybe we could ask her to, because I don't know how deeply she wants us to know, like, what we're talking, like, what is it talking about. I'm guessing she will, because it's a kind of concept sort of thing. So if we get this wrong, we might get something else wrong. We don't know. Oh my goodness. Okay. So yeah, I'm not sure. I don't. Yeah. Let me try.
Yeah, that's a question that we definitely need to ask because that's the only thing I'm confused. I don't know how would that. I don't know. Just I'm a little confused on that one.
Because I don't know where it's coming from, or like, is it the synapse? Like, what is it? The synapse? Like, we don't.
Yeah.
Yeah. So this is the last slide, other than this one that she talks about. So I'm guessing we're going to talk about this next time, acetylcholine and all that stuff. Yeah.
So what she goes over on Friday, like finishing up this chapter, is all of this going to be on our test, or is she just stopping at what we did last Friday? I'm just confused.
Said she was stopping at what we did last Friday.
Okay, thank God.
Saturday.
Okay.
I hope.
Yeah.
Yeah, because I haven't even taken the new notes for the neuro stuff, and I'm like, I don't know when I'm gonna take it if I'm focused on studying for the test. Especially if like the neuroanatomy is like all the pages that I printed out.
I mean, at least we have Dr. Berryhill, and she's like, know this, know this, know this. Like,
yeah.
So that kind of narrows it down, hopefully.
Someone said last time, she was like, oh yeah, you guys don't need to know this. It's too advanced. I was like, yes, all right, bet. I mean, I know all of it's talking about, it's all reviewed. Like the layers of the skin. He was like, yeah, you don't need to know that. It's too advanced. Like, yes. But I looked at the PowerPoint for the neuro, and all looked super advanced. So I don't know if she's gonna go like, oh, you gotta know that this is this part of the brain, and like that's it. You're good. I hope it's like that. Anyways, so does anybody have any questions? Like, I know I'm gonna bring this up to her in class. I mean, I won't be in class, I'll be on Zoom, but whoever's in class or somebody will bring this up to her and ask her if she could please explain it again. Does anybody have any questions about anything else?
I don't think so.
Yeah,
It's just really like repetition and going over everything.
Okay, so I'm gonna stop the recording. Alrighty. I almost did.